Hello, this is Sanghoon Kim. I present a paper named A Conversational Approach for Modifying Service Mashups in IoT Environments. Let me start the introduction with what is a service mashup. There are many functionalities in an IoT environment, and users utilize these functionalities to accomplish their goal. Several studies suggested the IoT service mashup method to combine them as services, such as if a triggering condition is met, then do several actions like the right side figure. In addition, users want to speak out commands to create, modify, or remove a mashup whenever they need it. So some studies propose a conversational approach to create service mashups. That is, if a user says a desired behavior, the agent translates it into an executable mashup. One important thing is, users often modify mashups because they aren't professionals. To modify mashups through conversational interfaces, users should listen to the list of mashups and select one of them. And this causes several usability challenges. For example, the user feels hot even with an air conditioner, so she tries searching by device keywords, air conditioner, but she must listen to all the mashups related to the air conditioner. It's inefficient and imposes heavy cognitive load for processing this lengthy response. Thus, we propose Comma. Comma has a two-step interaction process, an implicature-based mashup localization, and a modification interaction with a disambiguation strategy. Let me talk about each step. As introduced, the naive approach has usability issues due to lengthy interactions. So we use implicatures, the implied meaning in the user utterances, to localize service mashups. A user can start searching mashups by simply expressing an implicature. For example, it's too hot here. This is another example of a localization interaction. A user hears an irritating noise, so says an expression, I hear a noise, and comma searches for a mashup that needs to be modified. To make this interaction possible, we face several questions. First, the types of user utterances. Second, the types of environmental properties. Third, the overall architecture for the localization process. For the types of utterances, we refer to studies from the pragmatics area that imperatives and expressives convey intentions to change the environment. We also support interrogatives as mixtures of imperatives and expressives. For the environmental properties, we refer to EUP ontology. It has 6 properties as shown in the figure, and IoT actions either increase or decrease the properties. For example, disable heating system action will decrease the temperature property. Finally, for the overall architecture, we propose an implicature-driven backtracking process. The core idea of this process is, first the user implicature and keywords are extracted from the speech. Then this information is used to query the mashup history for retrieving the mashups to be modified. Now we can move to the modification step. In this example, the user found that the noise is from unexpected vacuum cleaning action. So the user says a modification command, could you make it triggered at 10 a.m.? And the modification is made after a few follow-up questions. There are several design considerations to make this process: the types of modifications and the follow-up questions. For the types of modifications, we identify 4 main categories. That is, users can append, replace, modify, or remove a trigger or an action component. From these categories, we found that these 4 pieces of information are required: the type of services, the additional keywords, the position to be modified, and whether it is being replaced or appended. One issue here is, users can simplify their commands by omitting some required information, or even using irregular grammar, and this causes the ambiguity issue. Comma asks us a few follow-up questions to make them clear, but this could make the interaction longer, so we have to minimize the number of follow-up questions. We devised a disambiguation strategy to minimize it. We first check if the user tries to change the parameter, and if not, we disambiguate the position and the replace or append information. Here, contextual information, such as the current service mashup or conversation records, is checked, and if the information is not applicable, then a follow-up question is made. We finish it looking through the comma, so let's move to the evaluation section. We compared comma and the visual baseline, Samsung SmartThings, and we collected the time spent on each step, the number of interactions, task workload, and usability score. We prepared 3 difficulty levels, easy, normal, and heavy. Each level had a different number of IoT service mashups, that is 4, 7, and 10. Starting from the task completion time, we found a statistical significance only for the heavy task session. The baseline required lower modification time, but comma required significantly less localization time. Let's check the number of interactions for deeper investigation. Shown in the left side figure, the number of screen transitions spent on the localization doubled from the normal to the heavy task session. We think one reason is because the number of mashups for the session exceeds 7. It's known that the short-term memory capacity of a human is 7 chunks. However, for comma, the number of conversation turns is consistent for all task sessions. Lastly, the task workload and the usability score. Comma was perceived to be easier than the baseline for the heavy task session, and in overall, the usability scores were not too different. So, finally, let me conclude the presentation. We presented comma, a conversational approach to modify service mashups. Comma has a 2-step process, the localization and the modification interaction for users to easily modify mashups. Our user study showed comma is easy and convenient to use. In particular, the localization interaction was effective for modifying mashups. This is the end of the presentation. Thank you for listening, and please contact me if you have further questions.